Hello and welcome to another episode of our lecture series. Today we're going to go over some basic quantum algorithms that demonstrate the utility of quantum computing. So before jumping in, we're going to go over some preliminaries, some preliminary properties of the Hadamard gate, in particular the n-qubit Hadamard gate. So as you know, your standard Hadamard single qubit Hadamard gate is defined as this 2 by 2 matrix. And if we apply this matrix to these two basis vectors, we get the following basis vectors. These are denoted as the plus and minus states, and these happen to be the eigenvectors of the Pauli X matrices, which is why they're also called the X spaces. Now, if we expand this to 2 qubits, we use the property of tensor products here to write this expression here. And then we just take the tensor product of these two states, the 2 plus states in this case, and we get this result. And for the minus state case, we get this result, of course, multiplying everything out. Now, if we label these states as 0, 1, 2, 3, we can represent the state in this form and in this form. Now, if you continue, you start to see a pattern over here. So for the n-qubit case, if we take the tensor product n times, we take the tensor product of the plus state n times. And then what results is basically the sum of every single possible n bit string over here. So for starting with all zeros, we slowly add our way up until this final state of all ones, and we simply sum that. And then we, of course, add this normalization factor to make sure that its norm is 1. So basically, it's the superposition of all of these different states. And we can use this property to solve, well, to evaluate some quantum algorithms. So expanding this to the X binary string, well, before I move on, let me just slightly derive this for you. So it would be well, never mind. I don't think we need to do that here. Just move on. So let's say that instead of 0, we have this n-bit binary string. So what would happen here? Well, if you notice that we can write the value of the result of the Hadamard gate applied to the 0 and 1 states, we can rewrite this as minus 1 to the power of k being multiplied by the 1 state and added to the 0 state. So basically, the sign of this minus 1 to the k determines on which state it is. Well, we can use this notation to represent the superposition in this manner. And if we multiply everything out, you'll notice we'll see a pattern here. So for 0, 0, 1, we just get x0, 0, 0, 1, 0, we get x1, 1, 1, and you notice that this power here is actually, if we say this bit string is y, this pattern is actually just x multiplied the product of x and y over here, right here. So this is the final state we get. And this is another second important property that we'll be using in our proofs. So moving on, the first algorithm we're going to cover is called the Deutsch-Josa algorithm. So the Deutsch-Josa algorithm aims to solve the following problem. Let's say we have a hidden Boolean function f, which takes n-bit binary values as the input and returns either 0 or 1. So this function is what's called an oracle, which basically gives the answer depending on a single input. So an oracle basically checks the answer to some problem. And let's say the answer to some problem is a n-bit string. And it outputs 1 if the answer is, of course, correct and 0 elsewise. So this Boolean function can be seen as an oracle. Now we are promised that this oracle is either constant or balanced. Either that it returns 0 on all inputs or 1 on all inputs, or it returns 0 for exactly half of the inputs and 1 for the other half. So the problem is to determine if our oracle is constant or balanced. Now, this is just an example with 3 qubits. So we have 8 possible bit strings over here. And of course, in the constant case, it doesn't matter which bit string you put in, we always get the same value 1. And in a balanced case, 4 of these bit strings will give us 0, and 4 of them will give us 1 over here. Now, let's say we have a classical algorithm. So how can we solve this? Now, for returning to the 3-bit string example, we would have to at least let's say that f is balanced. Now, in the best case, we input these bit strings one by one, and it's basically balanced if during our process we encounter a value that is different. So in this case, we keep getting zeros. But if we get at least one entry that is 1, we can just simply stop right there because we already had information that there are only 2 possibilities, that it's either constant or balanced. And if we get another value, then it's obviously not constant. Now, to check if it's constant, we would have to basically check at least 5 values. Because if it was balanced, we wouldn't get the same entry for over half of the possible bit strings. So if we get 1, the same value for 5 different queries, we can assume that it's constant. So either way, the worst case and the best case, if we simply get lucky, we can simply answer the question in 2 queries if it's balanced. And in the worst case, we have to at least give it 5 queries. So generalizing this to n bits, we can say that the worst case is half plus 1 query, best case is 2 queries. So basically, our classical algorithm requires at maximum an exponential amount of queries per qubit. However, if we use a quantum algorithm, we can actually speed this up to only require a single query. So this algorithm is an example of what's called quantum advantage, which is where a quantum algorithm shows a significant speed up in comparison to a classical algorithm. So the Deutsch-Josa quantum algorithm, Deutsch-Josa algorithm quantum circuit, looks like this. So we first prepare n qubits in the 0 state, and we prepare also an ancilla qubit in the +1 state. And then we're going to apply Hadamard gates on each of these. So what we get is basically, as we saw before, a superposition of all the possible bit strings, tensor product with the plus minus state over here. the minus state over here. And then we put our result into what's called our oracle, of course, our unitary oracle, which basically performs the following action. So for the upper data qubits up here, it just returns the same value. But for the ancilla qubit over here, it returns y and adds it to the result of f of x. So plugging our state psi2 into here, this remains, of course, unchanged, but we have to apply y at f of x minus 1 at f of x for each entries over here. And if we expand this expression, we get this expression right here, of course. And then we use a clever rewriting of this state over here to represent it as this. Here we've ignored the last qubit, which is in this state here over here. So finally, we apply n Hadamard gates on the data qubits only, and we use this property over here. So ignoring the last qubit, we get this state over here. And using this property, we could rewrite this value over here in terms like so. And then we can combine this over here. So analyzing this final expression, we have two possibilities. First, f of x is a constant function. If f of x is a constant function, then for the probability of measuring the zero state over here, if we put y 0 over here, we get minus 1 f of x squared over here. And if f of x is a constant function, this will either be minus 1 or 1. So this all adds up to 2 to the n, and this will be 1, of course. But if it's a balanced function, half of these values will be 1, half of these values will be minus 1, resulting in 0. So basically, when we get our final state, we just have to measure the data qubits, and if we get a final state of 0, all 0, of 0 for our ancilla qubit, no, not ancilla qubit, our data qubit, if we measure all zeros, then we can conclude that it's a constant function. And if we don't measure it, we can conclude that it's a balanced function. So the next algorithm we're going to cover is what's called the Grover's algorithm, or the quantum search algorithm, which is basically a quantum algorithm for solving the unstructured search problem. And this gives us a speed up, a quadratic speed up. So just to remind you, an unstructured search problem is basically searching different possibilities for a certain solution, of course. So let's say we have several different boxes with n different boxes, and we want to find a marked box. So using classical computation, we would have to check on average half of these boxes, in the worst case, of course. And in the worst case, we have to check all of them. So it's scales of ON. But using quantum computation, we can actually speed it up to solve this in O to the root of n. So this is the formal problem statement. So for 2 to the n, we have this oracle over here that says detects whether it's a solution. And let's say there's a unique solution out of all the different possible bit strings. And in this case, f of x equals 1. So our goal is to identify omega, this unique solution. And of course, we have access to the function by what's called a query gate, which basically, as we saw before, outputs this value. Basically, its role is to output the value of f of x. So so this is the basic procedure for Grover's algorithm, which uses this nice property. So let's say y equals the minus state. And then we can input this into UFF. And according to the definition, we can expand this expression into here. And then we can rewrite this as this. Because f of x only has two cases, which is f of x equals 0 or f of x equals 1. And if f of x equals 0, of course, we get the minus state. And f of x equals 1, of course, we get negative this minus state. So we just have to put this factor over here, and we can rewrite this final state here. So let's now define a operator S of f that conditionally changes sign of the amplitude of the good state. So if f of x is 1, we get minus x, and f of x is 0, we get x, basically. So operator 0 changes the sign of the amplitude of the state 0. Of minus, so if x is all zeros, then we get minus 0, of course. And if x, and we just get the state here if x is not 0. And this operator can be represented as so, of course. So these are all the pieces of our puzzle. And now we can reconstruct Grover's algorithm using these pieces. So first, we initialize the n-qubit register to the all zero state. And then we apply the Hadamard operation to each qubit of the register, which gives us this superposition of all the possible different bit strings. Now, this state will contain our solution bit string that we're looking for. So let's isolate it over here and rewrite this state over here. Next, we apply t times the following unitary operation, which is g. And g is defined by s of f, which we defined earlier, which conditionally changes the sign of amplitude in the good state if it's a solution. And S0, which is defined as this operator over here. And we, of course, sandwich these between these two n Hadamard gates. And what this operation basically does is it rotates the final state over here towards the solution state. So this state can be, if we represent this state as omega perp and this state as omega, what it's basically doing with each application of the G is it's rotating it by some angle theta, which is defined over here. So let's go through this step by step. So if we apply S of f, what happens is that it reflects it around this omega perp, the final superposition state S. Because it's minus x if it's f of x equals 1, and x if f of x equals 0, not a state. So basically what happens is that if we apply this to S, we of course get this, and then we get this over here, which is just, this is just negative. Over here. So basically, we're flipping this around this axis. And now if we apply this operator over here, what happens is that we're doing another reflection around this operator over here. So S of 0 is defined at this state, but if we sandwich this between these two Hadamards, what we get, of course, is the superposition of all the different bit strings. And this is defined as flipping it around the state S. So what we're actually doing is re-rotating S by this angle, theta, by an angle to theta, I mean, sorry. So applying G once rotates this by 2 theta, applying it twice rotates this by 4 theta, and we keep applying it until, of course, we reach our solution, omega. Or at least until this vector is closest to here. So ideally, we want the final angle to be, of course, 2 pi over 2, which means it's exactly equal to omega. Sometimes this is not the case. Sometimes we rotate it too much and we actually go past omega. So that's one caveat of using Grover's algorithm. A lot of iterations may not actually be optimal. There's a sweet spot in which is closest to our solution. So sine theta is square root to the n over L, of course, because of our definition of S. And so when n is large enough, theta gets close to 0. So for very large n, we can approximate it as this. And then if we plug and chug this into here, we can see that number of iterations we require for it to be pi over 2 is that it is, of course, proportional to the square root of n. And of course, you can actually expand this algorithm to many different solutions. M, and it turns out that in this case, Grover's algorithm is actually proportional to the square root of n. So that's all for this lecture. See you guys next time.